Hi everyone, my name is Milad and today I'll be doing a system design practice exercise. I'm doing these to help improve my skill set and I hope in that process you guys learn something as well. Remember, double check anything you see and hear in my videos. There are people far more experienced and fluent in system design than I am. If you do enjoy the video, I hope you decide to like, subscribe and leave a comment. Alright, with that let's dive right into our design. Today I'll be focusing on building a search engine. My requirements are as follows. Provide relevant URLs for a search query. Sort results by relevance and popularity. Ensure minimal latency and maintain high throughput. Continuously crawl and gather web data. Because our data for this system is going to be pretty flat and simple, I'm going to use a NoSQL database like MongoDB. In MongoDB, instead of tables and rows, what you have are collections and documents. So let's design our data because that's what I like starting off with. It gives me an idea of what kind of entities I'm working with. So one of the things we'll definitely have are URLs. We'll have URL ID. We will have URL, the actual URL. We will have a status ID, and we will have a hash of the URL we can use to, what we'll use that for is potentially sharding down the line, and that's good for now. And then what I'm going to do is also focus on the data of that URL. Because remember, pages are dynamic and they're constantly changing. We have to ensure that we are maintaining, watch on those pages to see when they change. So we're going to call this URL data or URL content. So we will have a URL content ID. We will have a URL ID. We will also have the status of this. If it was, for example, we can use the status for whether it's successful or not. We will have a hash of the content. We will use that to determine whether the data has changed, and if so, process that information. And then we'll look at the content. In our content, we will have title, description, HTML, and then we can have assets here. And these can be images, videos, audio, and other. Alright. We will also have links within URLs, so we'll call this links. And we will have links here. Will be just basically a collection of links. We will have a dateStamp, and I think that's a good start here. Am I missing anything? Not that I can think of. We can potentially, if we wanted to, have the keywords that we've extracted out of here as well. And remember, these won't be the actual assets, but links to them, links to these assets. And then here we would have a keyword and the number of times that keyword occurred. And once again, this would be a list. Alright, I think that's a great start for what our content would look like when we're crawling it. And then of course we have keyword. We'll have, oops, we'll name this keywords. Let's maintain consistency here, URL contents. We will have keyword ID, keyword, and we can have, so in here we will also have URLs associated with these keywords. So for each instance here, we will have a URL ID and count. So this is what our keywords collection would look like. Here, there's a potential, well, it's definitely a potential issue here, is certain keywords will have many hundreds, millions of, tens of millions of URLs associated to them. So what we do when you use MongoDB is you break up that massive data set under one specific keyword into buckets. So what you would do is you would sort all the URLs that contain that keyword and then create a rating. Right now we have count, but we can also have some rating, and that rating can be an algorithm we decide, and this will help us with sorting results by relevance and popularity. That relevance and popularity would result in a rating, and that rating is what we would use to sort these URLs by. So the first bucket for one keyword would be the URLs with the highest rating. The second bucket would be the next set with the second highest, and so forth. So this is what our data would look like, and we will have three different databases. And we will have the URL DB, NoSQL. We will have a keyword DB, NoSQL. And we will have a content DB, NoSQL. Now, there's an argument to be made that when you crawl the website, you might want to save the HTML and the content into a data store, like a blob storage, and that's possible. It really depends on how you want to approach this and what suits your needs the most. All right, with that said, now let's take a look at our API. Our API would simply be a get. We did our API search backend. Our parameters would simply be the query, and whenever you are searching, you always want an offset, so that when you click, if you have pagination, you know, you can tell the backend where you are. All right, so now when we talk about a service like a search engine, we know right away that we'll be servicing this around the world. And given that we want to ensure minimal latency, we want servers and data centers all across the world on every continent. So to start off with, we're going to start off with a global load balancer. And this will, as soon as you type in, let's say google.com, it'll direct you to one of these global load balancers. And then the global load balancer will use a very simple algorithm to determine where to direct you to next. In this particular case, it will determine which regional load balancer would be most appropriate for you. And this would be very simply, potentially the one with the closest geological location, the lowest latency, or if a system is down. After the regional load balancer, we're going to go ahead and pass that into a local load balancer. Now, local load balancers exist within your data center, and they route the request to the most appropriate server based on whatever algorithm you choose. From the regional load balancer to the local load balancer, you can use round robin, lowest latency, least load, weighted round robin, and the same thing with the load balancer, local load balancer. Once we get a query, we always have to make sure that we never trust the input coming in from users. So we want a service that normalizes the data. And what this will do is it will capture the request, and it will ensure that everything is lowercase. It will ensure that all the words are stamped, meaning they're brought down to the root word. And then it will take those and break them up into all the keywords and remove words that we don't use for searching, like and, to, there. So once we've done that, we pass this on to the search service. The search service will then search for URLs that are associated with those key terms. And for us to hit the database would be really a poor decision, because first off, we can overload our databases and it's not fast enough. So what we want to do is utilize cache. Cache is a service that allows us to save data in memory. And in memory is one of the fastest way to save and retrieve data. A service that provides that is called Redis. So this would be our keyword cache. Provided through Redis. Now what we do is we get the results. We search for keywords, and then when all the results come back, we try to see where all the keywords cross, and then get those URLs, and then sort them by the rating and return those results back to the client. But since we are only saving the URL IDs, what we want to do next is have another service, cache service, that holds our URL data. Once again, another Redis server. So once we get the URL information, we'll grab the URL. Once we get the URL identifiers, we're going to get the URL information from our cache. Every time you introduce an additional service, you are adding complexity, additional failure points, but you're at the same time creating a level of fault tolerance and ensuring that you got separation of focus here. If the search engine, the search service does not find any keywords in the cache, it will then hit the database, keyword DB, and likewise, if it does not find information about the URL in the cache, it will hit the URL DB. and then we will return that information back to the client, and that is our first step towards processing a request. Now, when we talk about scalability, one of the things, as I mentioned, is we definitely want to shard our databases, and we want to shard them based on a specific key. So basically what sharding means is that you take your data and you distribute it to different database servers, and you distribute them based on a specific criteria, and that criteria would be a specific value, a key in your collection. For example, you can use the hash value in URLs, the URL itself, and then you distribute that to a specific server that's designated for that specific key or hash. One of the ways you can do this is use consistent hashing, which allows for dynamic adding and removing of servers. In addition to this, all our databases will be on separate database clusters distributed in the data center as well as across the world. This allows us to have redundancy, backups, and failovers in case of anything that happens. Same thing with our caching servers. We want to definitely ensure that we provide them as a cluster, and that cluster allows us to provide redundancy, ensure that we always give you the fastest service. In addition to that, we will also partition the way the data is saved into the cache, following the same type of consistent hashing to ensure that we distribute the load and make retrieval much faster. Because if a single server has all the data, it's very hard to find the information, and the scale of those servers would be astronomical, probably much more than anything that would be practical with today's technology or even tomorrow's technology. All right, the next thing we want to focus on is crawling. So we have our World Wide Web, and we want our crawlers to hit the World Wide Web. We will have many crawlers, and we spin them up and spin them down as necessary, and each one of them will be responsible for crawling one specific URL. So these crawlers will be subscribing to topics, so what we want them to do is listen to a specific service that messages are published to, and these services will subscribe to those services. So a service that I'm familiar with is Kafka. It's a message broker, and basically it's like a stack where you dump data in, and then on the other end there are services that are listening to the topic, and they will act on those topics, act on those messages as they come in. So we have the crawlers that listen to get the URL. They're subscribed to the crawl URL topic. When they get a URL, they will hit the web and get that information. And then once they have that information, what they will do is they will write that information onto a different topic. And this will be our new crawl content. Topic. And once again, this is a service provided by Kafka, And what we will have here is the raw HTML that the crawlers acquired from getting the content from the URL. So over here we will have services that subscribe to this topic and process content process. We will have, once again, hundreds, thousands of these services that are subscribed to this topic, and they will read that content, and the first thing they will do is extract, just like the normalizer. We will, let's do this. We will first find assets. Normalize. And then, so the first thing the content processor does is it hashes the value and checks the content DB to see, actually, now that I think about it, let's get rid of this. Let's have another cache server here. We will have a Redis server that caches the content, and caches the content hash and URL. Let's see, what do we need? Hash should probably be named content. And URL ID. So the first thing it does, it will check the cache and look up that URL and see that content hash URL, and if it has changed, it will then find find asset service that will find all the assets. Then it will call the normalize service, which will extract all the keywords, turn them into lowercase, and stem them. And then finally, after all that is done, it will write to another topic all the information related to that. Then over here we will have a save and update service that will subscribe to this topic, and then it will update the content DB. It will update all the databases. DB. I'll separate this so that we have two different ones, and then update cache service. Oops, what is that? And we will have another service that once again subscribes to this topic. And its responsibility is to update the cache. Additionally, one thing is we also want a rating service. The rating service will figure out how to score each URL with a specific keyword. Now, once again, this could be a combination of where the keyword occurs, where, how often the keyword appears, what kind of style it is, and many other factors that can be taken into account. That is an algorithm that you will, or a model you will play around with to ensure that you always get the best results. Alright, so let's take a look here. Provide relevant URLs for search query. We've done that. Sort results by relevance and popularity. We've done that. Ensure minimal latency and maintain high throughput. We've done that. And ensure and continuously crawl and gather web data. Okay, so probably one thing that's missing here is what is populating the crawl URL topic. We will have a service. These will be publishers, and it will schedule URLs for crawling, and it will look at the last time. Actually, let me get rid of this. So I think what we could do is waiting URL topic. So what will happen is when we crawl, because we always want to continuously crawl URLs, after we crawl it, we will write it back. We will write it to a waiting URL topic, and then we will have a scheduler that we will have schedulers that subscribe to this topic, determine what should be crawled next, and then write those to the topic, crawl URL topic, and it will be a recurring cycle. And we can have a job that will always ensure that will subscribe, that will always and will have an idea of all the URLs, and then check when the last time the URL was scheduled, and if it hasn't been scheduled in a while, write set to the topic, waiting URL topic. Alright, and when we talk about scalability, another thing is worth mentioning is that all our services will be built on top of an auto-scaling Kubernetes infrastructure. So each service would be operated in a Kubernetes node inside a pod, and that node will scale pods up and down, firing them up and terminate them depending on specific configuration. And if a specific node has reached its limit, the auto cluster will add an additional node as necessary to handle the load. So all our services would be configured in such a manner. And for our topics, we would definitely partition our topics. And when you partition a topic, it means more subscribers can read from that specific topic. So if you have 100 instances of content processor service, you want to make sure you have at least 100 partitions, so that no subscriber is sitting idle. Alright guys, that is my attempt at designing a search engine. Please let me know what I did right and what I didn't do wrong, what I did right and what I did wrong, so that I can improve my skill set as well. Thank you so much. Have a wonderful day.